Now, let us study the combination of capacitors. Capacitors can be combined, series or parallel. First, let us discuss capacitors in series. Three capacitors of capacitance C1, C2 and C3 are connected in series. A potential difference of V volts is applied across the combination with the help of a battery. A quantity of charge Q flows to the first plate of the first capacitor. The other capacitors are then charged with the same quantity of charge by induction. The potential across the capacitors are V1, V2, V3. By the law of conservation of energy or by superposition principle, the total applied voltage V is equal to V1 plus V2 plus V3. From the definition of capacitance, we can write V is equal to Q by C, V1 is equal to Q by C1, V2 is equal to Q by C2 and V3 is equal to Q by C3. Substituting these values, we get Q by C is equal to Q by C1 plus Q by C2 plus Q by C3, where C is the equivalent capacitance or effective capacitance or net capacitance or total capacitance. That is, if we replace three capacitors by a single capacitor of same charge by applying the voltage V, then the effective capacity or capacitance will be C. Now by simplification, we will get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. If we have many number of capacitors, in general we can write 1 by C is equal to sigma I is equal to 1 to n 1 by Ci. Therefore, the effective capacitance is the sum of the reciprocal of the individual capacitors. Hence, the reciprocal of the effective capacitance is the sum of the reciprocals of the individual capacitance. Here note that the effective capacitance in series combination is less than the least of all the individual capacitance. Parallel combination of capacitors. Three capacitors of capacitance C1, C2 and C3 are connected in parallel as shown. A potential difference of V volts is applied across the combination. Being parallel combination, the potential difference across each capacitor is same. Let Q be the total charge drawn from the voltage source. On reaching the terminals, it split into Q1, Q2 and Q3. The charge is distributed in direct proportion to the capacitance. By the charge conservation principle, Q is equal to Q1 plus Q2 plus Q3. By the definition of capacitance, Q is equal to CV, Q1 is equal to C1V, Q2 is equal to C2V and Q3 is equal to C3V. Substituting this one, we will get CV is equal to C1V plus C2V plus C3V, where C is the equivalent capacitance. By simplification, we get C is equal to C1 plus C2 plus C3. If we have n capacitors in parallel, then the equivalent capacitance C is equal to sigma I is equal to 1 to n Ci. The effective capacitance in parallel combination is the sum of the individual capacitance. Therefore, the effective capacitance in parallel combination is larger than the largest of all the individual capacitance. We know that capacitor is an arrangement to store electrical energy. So let us have an expression for energy stored in a capacitor. For that, consider a parallel plate capacitor connected to a potential difference V. The process of charging a capacitor is equivalent to transferring charges from one plate to the other plate of the capacitor. That's why one plate becomes positively charged and other plates becomes negatively charged. The moment charging starts, there is a potential difference between the plates due to charge separation. Therefore, to transfer charges against the potential difference, some work is to be done. This work is stored as electrostatic potential energy in the capacitor. To find the total energy stored in a capacitor, consider a charge dq being transferred against the potential difference V. Then work done is given by dW, which is nothing but equal to the potential energy du. Therefore, du is equal to dW is equal to V into dq. By the definition of capacitance, we know that V is equal to Q by C. Therefore, du is equal to Q by C dq. This is the amount of work done to transfer a small amount of charge dq from one plate to another plate. In order to charge the capacitor to its full, or the amount of work done to transfer the total charge q, which is nothing but the energy stored in the capacitor, is given by U is equal to integral 0 to q by c dq. Now, being c a constant, we can take 1 by c out of the integration. Then you will have integral q dq, which is nothing but half q square by 2. Now, applying the lower limits and upper limits and simplification, we get U is equal to half q square c. This is the expression for energy stored in a capacitor. Now, we know that Q is equal to CV. Substitute it in this expression, we will get half C square V square by C. C square and C cancels, and you get another expression for the energy U is equal to half CV square. Now, C can be written as Q by V. Now, U will be equal to half into Q by V into V square. V and V square cancels, and we get one more expression, that is U is equal to half QV. So these are the expressions for energy stored on a capacitor. Let us see what is energy density. We got the expression for energy stored in a capacitor U is equal to half CV square. But for a parallel plate capacitor, we know that C is equal to epsilon 0 A by D and V is equal to E into D. Substitute both of these values in the expression for energy. You will get U is equal to half epsilon 0 AD E square. Now take AD to the left hand side. You will get U divided by AD is equal to half epsilon 0 E square. Here area into distance A into D is the volume. Therefore U divided by D is the energy per volume. This is called energy density. Therefore we get the expression for energy density as U bar is equal to half epsilon 0 E square. So SI unit of energy density is joule per meter cube. Energy density is generalized as energy per unit volume of the field. This says that the energy stored in the capacitor is in the form of electric field between the plates. That's why U bar is equal to half into epsilon 0 E square, where E is the electric field between the plates. So we know the expression for energy stored in a capacitor. Now let us see what will happen to this energy when two capacitors are connected to each other. For that, consider two capacitors each of capacity C1 and C2. Let Q1 and Q2 be their charges and V1 and V2 be their potential difference between the plates respectively. Then Q1 is equal to C1 V1 and Q2 is equal to C2 V2. When these two capacitors are connected in parallel, since there is a potential difference between these two plates, charge will flow from the capacitor of high potential difference to that of low potential difference. The flow of charge will continue until the potential difference of both capacitors becomes equal. This potential difference is known as common potential and represented as V. So, after connecting these two capacitors, the total capacitance of this system becomes C1 plus C2 and the common potential is V. Then the total charge Q becomes C1 plus C2 into V. When the capacitors are connected, there is no loss of charge but only sharing of charge occurs. Therefore, the total charge after sharing should be equal to total charge before sharing. We know that the total charge after sharing is Q is equal to C1 plus C2 into V, and total charge before sharing is Q1 plus Q2, which is nothing but C1 V1 plus C2 V2. So we can write this one as C1 plus C2 into V is equal to C1 V1 plus C2 V2. This is by the conservation of charges. There is no charge lost, only sharing happens. From this, we can get the expression for common potential V as C1 V1 plus C2 V2 divided by C1 plus C2. Initially, the first capacitor will have an energy of half C1 V1 square, and the second capacitor will have an energy of half C2 V2 square. Therefore, the total energy before sharing or before connecting the two capacitors is given by U is equal to half C1 V1 square plus half C2 V2 square. When we connect these two capacitors, their total capacitance will be C1 plus C2, and the potential will be the common potential V. Therefore, the total energy after sharing is U final is equal to half C1 plus C2 into V square. Now, let us find the difference between these two energies. Let us see whether there is a difference or not. Okay, so if you find ui minus uf by substituting the value for ui and uf, and after simplification, you will get the result as C1 C2 into V1 minus V2 whole square divided by 2 C1 plus C2. Here C1 C2 are positives. V1 minus V2 whole square is also positive. Therefore, ui minus uf is greater than 0, or it is a positive value, which implies that initial energy is greater than final energy. This proves that total energy after contact is somewhat less than the total energy before contact. Hence, there occurs a loss of energy, which is given by ui minus uf on sharing charges. This loss of energy appears in the form of sparking and heat produced in the connecting wires. So, we can conclude that when charges are shared between any two bodies, their potentials becomes equal. Charges occurred are in the ratio of their capacities. No charge is really lost, but some loss of energy does occur.